Let's take a closer look at these two types of oscillations. I want to look at the forces involved in the motion and see if there is something similar between them. So let me start by looking at the spring. Now we have learned about Hooke's law. For the spring, Hooke's law tells us about the force that pulls the ball back if I displace it. So let's say I displace this ball by displacement x in this direction. If I then the spring gets stretched and the spring will want to pull the ball back up with a certain force. Now Hooke's law tells us that this force is proportional to x, meaning that there's some constant, some fixed number k times the displacement. So what we understand from this force is that this law is that if the displacement is bigger, meaning if I pull the ball more, then there would be a bigger force that pulls it back. Whereas when the ball is at its rest position, there would be no force or no resultant force on the ball. So that's Hooke's law. So that's how it works in this case. Now let's have a look at the pendulum. So what's the force that pulls the ball back if I displace it? In order to do this, I need to draw a bigger picture. So here goes. Now at this is at the rest position. Ball is here, and at its displaced position, when I pull the ball sideways, let's say that the ball is here, is there. So what pulls the ball back? Obviously its own weight. Obviously, the force of gravity pulling down the ball is weight mg would want to pull it back. But let's try and be more precise on this. Now the ball, the weight is pulling downwards, but when the ball swings back, it doesn't go downwards. It swings sort of a bit slanted, a bit horizontally, right, back to its rest position. So it is actually not all of the weight of the ball that causes it to move backward. It is, so let's be more precise about this, it is a component of this force. So let me resolve this force into its two components. Now, but in which two directions? Well, I want to know what force actually makes the ball move. So I want to have one direction along here. Well, along here. Now what do we mean by here? Okay, to be more precise, the here means that it's in the direction perpendicular to the string. For the simple reason that the ball is not going to move along the string since it's held taut by the string. So that would be the component that causes the ball to move perpendicular to the string. Now, just for completeness, I'm also going to think of the component of the force, right, in the direction of the line of the thread. Okay. So I've resolved my force, my weight into these two components, one here and one here. So I can think of the sum of these two forces as being equivalent to the weight. So once I have resolved this weight into those two forces, I can pretend that the weight is not there, but instead I I have those two separate forces, and it's going to have the same effect on the motion. Okay, so we are here. All right. So looking at those two equivalent forces, all right, forget about this for the next few seconds. It is this component that causes the ball to move back to its rest position. The other component does not cause the ball to move. Not directly anyway, because this component is balanced, or if you like, cancelled by the tension in the spring. So that's cancelled. So that's why we are left with one, if you like, effective components that pulls it back. Okay. Now what I want to do now is this. I want to find out the value or a formula for this component. More specifically, I want to find out how this component changes with the displacement. How is it related to the displacements of the ball? The displacements x. Because I want to have some kind of formula that looks like the Hooke's law for this. Maybe not exactly, but I want a relation between this force, which I also call this F. Okay. So now I'm talking about the pendulum now. Okay. So let's see. How can we do this? Now the standard way to do this is to start by thinking about the angle, this angle theta. Okay, it's angle theta, and we think about finding, say, both this force and this x in terms of the angle, in terms of this angle, and then we try to relate the f and the x. Now the force might be easier to start. So first, notice that this angle is the same as this angle, because this is the vertical and that's the weight and they are parallel. So those two angles, that one and that one, are corresponding angles. So they're equal. Right? So therefore, if I want to find this component, and know that this is mg, what I do is I would draw a right angled triangle this way. I'll draw this right angled triangle, and then this side would be the same as this side because this is just a parallelogram or rectangle. So, and this side is related to, this is mg. It's getting a bit complicated now. This vertical force is mg. So if I want this side, I have to take this side, the longest side of the right angle triangle, and multiply by sine of the angle. So therefore the force is equal to mg, which is this longest side, multiplied by sine theta, and that gives me this side. Okay, sine theta. Okay, so I have force in terms of theta. Now next, let me try and find x in terms of theta. Okay, how do I do that? So again, I probably need to use sine again. That length. Okay, the length of the string, I'll call that L. Let's say L is the length of this string, and I want to relate x to theta, right? So x is also this distance. I can also draw the distance, the displacement x here. A horizontal line from the ball to the vertical. So that's a right angle. So therefore that is also x, but that is also the side of this right angled triangle, where the longest side is L. So we can now see that x must be equal to L times sine theta. So let me write that down. X must be equal to L times sine theta. So that's convenient because I've sine theta here and I've sine theta here. And as I said, I like to find a relation between f and x. So the way to do it now is to somehow get rid of sine theta. And in algebra, we can do that quite easily if we divide the two equations. You see, I have these two equations here. Okay, if I divide the left side by the left side, that, and if I divide the right side by the right side, like this must be equal, right? Because the separate parts are equal. Therefore, this must be equal. Now, why would I do that? Because if I do that, I have sine theta on top and sine theta at the bottom, and they can divide out, they cancel. And that's nice because I really just want a relation between the x, the displacement and the force. I'm really not that interested, at least not now. I'm not so interested now in the angle. And apart from that, I have m, g, and l. Those are alright. Those are just constants. L is just the length of the string. I can easily measure that from the ruler, with a ruler. M is the mass. I can just weigh it. Okay, I now know what g is. So these are numbers that I can easily find out if I have a pendulum. So therefore, now I have my equation. I have my equation, and let me write it in a way that looks a bit like the Hock's law, with f as the subject, and I'll move x to the other side and just multiply both sides by x. This is what I have: mg L over x. So we have a nice simple formula relating x and f. And the main point I want to make here is that if you look at those two equations, you see that you can see the similarities. Okay, this one looks more complicated. Okay, but let me point out the similarities. The similarity is that in the two cases, the force is proportional to the displacement. Now, if you remember what proportional means, it means that it is equal to x. That means the force is equal to x times a fixed number. Now, see, this number is fixed. When we say fixed or constant, it doesn't mean that it is forever or is constant in all situations. It just means that in this particular example, if x changes, if you have a different displacement, that number does not have to change. Okay, the mass and the length can stay the same if I string this pendulum and the x changes. So these are constants in that sense. Likewise, for the spring, if I am looking at the same spring, then as x changes, okay, the restoring force is going to be obtained by multiplying by the same k. So in that sense, in the two cases, force is proportional to x. And we know what proportional means. It means, for example, that if x is doubled, the force must be doubled. If x is increased by 3 times, the force must be increased by 3 times. So we see this common property, this nature of the relation between force and displacement is exactly the same for both the pendulum and the spring. There's an additional point I should explain before leaving this. Now, I've pointed out the similarities between the relation between force and displacement in the pendulum and in the Hock's law. But what I want to point out now is this. Whereas in the spring, in the case of the spring, you see that the displacement x and the restoring force are both along the same line. Now, as I've drawn this picture here for the pendulum, my displacement x, I've drawn it as a horizontal displacement, but the force, you can see from this picture, is clearly not quite horizontal. It's at a slanted position. Okay, it's at a slanted position. So this force is actually, let me make a note here. This is slanted. There's a slope in the force. Okay, this maybe let me call it tilted. The force is slightly tilted, and this x here is horizontal though. Horizontal. Okay, so what this means is that the two situations are not exactly the same. They're not exactly the same, but in the case when x is quite small, the angle will be quite small. This line, this displaced line, would be quite close to the rest position, will be quite vertical. So if the angle is quite small, or if the amplitude of the motion is quite small, the force would always be quite horizontal. The force F would always be quite horizontal. Okay, so for this purpose, because the meaning of the F, in the equation is not exactly the same. In this case, they are both in the same direction. In this case, it's in a slightly different direction, but the F is approximately horizontal if the angle is tilted. I'm going to use say that this is approximate. They are approximately equal. So we know that this is approximately equal for small angle. Okay, because we really ought to be comparing the component of this force in the horizontal direction. Okay, but I shan't go into the details of the mathematics, because for our purpose we just need to be aware of this.